One of the big keys to be successful in trigonometry is identifying all of the different ways that the trigonometric ratios relate to each other. They are related through a bunch of categories of identities known as fundamental identities. There are going to be 4 different categories of fundamental identities. The first category of identities is known as reciprocal identities. You probably noticed as we were listing all 6 different trigonometric ratios that most of these trigonometric functions can be expressed in terms of reciprocals of each other. Cosecant, for example, was the hypotenuse over the opposite. The reciprocal of that would be the opposite over the hypotenuse, which is known as the sine of theta. Now that's typically the only one that gets written down, but technically the reciprocal identity could also exist in the following form. The sine of theta is the reciprocal of the cosecant of theta. Additionally, the same thing exists between the secant of theta and the cosine of theta. Secant of theta is the hypotenuse over the adjacent, which is the reciprocal of the adjacent over the hypotenuse. And again, this can also be expressed in terms of this form. Cosine of theta is 1 over the secant of theta. Finally, the relationship between the cotangent of theta and the tangent of theta in terms of the adjacent side and the opposite leg exists as well. So, cotangent is the reciprocal of the tangent, and tangent is the reciprocal of the cotangent. So, these relate to the opposite and the hypotenuse. These two refer to the adjacent and the hypotenuse, and these two refer to the adjacent and the opposite. So anytime you're pairing off in terms of 2 sides, you'll know which identities you can use. Next up, quotient identities. There are 12 quotient identities. This is where the ratio of one trigonometric ratio to another trigonometric ratio yields a third trigonometric ratio. We're not going to do 12. We're only going to do 2. And the 2 that I want to use are the sine of theta divided by the cosine of theta. Putting these in terms of the ratios that we know, sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Dividing by a fraction means that you can multiply by the reciprocal, and we can see that by multiplying by the reciprocal we can cancel out the h's, leaving us with opposite over adjacent. Opposite over adjacent would be the tangent of theta. So more commonly you're going to see this written in the following form. The tangent of theta can be expressed as the sine of theta divided by the cosine of theta. Additionally, if we were to start with the cosine of theta divided by the sine of theta and attempt to do the same thing, this would be adjacent over hypotenuse over opposite over hypotenuse, which is adjacent over hypotenuse times Once again, the h's cancel out, and you'll be left with the adjacent side over the opposite side, which is the reciprocal of what we just had. The reciprocal of tangent is cotangent. More frequently, you'll see this written as the cotangent of theta is equal to the cosine of theta divided by the sine of theta. Bing, bang, boom. Next up, after the quotient identities, there are 3 Pythagorean identities. There is one super important Pythagorean identity that you absolutely will need to know. There's one that you'll use like 20% of the time, and then there's one that you'll use like 1% of the time. So for the Pythagorean identities, I'm going to start by expressing the Pythagorean theorem in its brand spanking new form in terms of the opposite leg, the adjacent leg, and the hypotenuse. So O squared plus A squared is equal to H squared. The 3 different Pythagorean identities that can be created come from dividing by one of the 3 terms that is present in the Pythagorean identity. So for example, if I wanted to divide by H squared, I would get O squared over H squared plus A squared over H squared is equal to H squared over H squared. We'll come up here to continue to simplify. O squared over h squared, I can factor out the square and call this O over h. Factor out the square here, we'll call that A over h. And then h squared over h squared will simply be 1. Now O over h, that would be the SO of SOHCAHTOA, so that would be the sine of theta squared. A over h is the A, or Ka, of SOHCAHTOA. That'll be the cosine of theta quantity squared. So when you square the sine of theta and add it to the square of the cosine of theta, you get 1. The typical notation that you see for take the sine of an angle and then square it will be the following. To indicate that you're squaring the sine of the angle or the cosine of the angle, the superscript 2 gets put right here. Never use this notation. Never use this notation because it's not clear whether we should be squaring theta then taking the sine or taking the sine of theta then squaring it. So that's a big fat no. Don't be that person. Definitely don't want to be that guy or gal or individual. Now, there are 2 other Pythagorean identities, and the way that we are going to create said Pythagorean identities is by dividing by one of the other 2 terms that's located in the Pythagorean identity. So for the second one, we are going to divide by, let's do a squared next. So we started with O squared plus a squared is equal to h squared. We're going to divide all 3 of these terms by a squared. Then I'm going to do the same tricks that we did just a moment ago. Factor out the square. This will be O over a, quantity squared, plus a squared over a squared will be 1. Then we'll see h over a, quantity squared. Opposite over adjacent is the tangent of theta, which we then square. 1 stays as 1. Hypotenuse over adjacent would be the secant of theta, which we will then square. That is our second Pythagorean identity. The third Pythagorean identity comes from dividing through by O squared. So O squared over O squared plus A squared over O squared is equal to H squared over O squared. I see a ho. O squared over O squared reduces to 1. A over O quantity squared will be the cotangent squared of theta, and, well, cosecant's a ho, so it'll be the cosecant squared of theta. So, 3 Pythagorean identities involving the sine and the cosine, tangent and secant, cotangent and cosecant. Finally, the 4th type of identity is referred to as the cofunction identities. For the cofunction identities, I'm going to introduce some terms for you. Given a right triangle, the 2 other angles that you have that are contained within your right triangle are referred to as complementary angles. I'm going to call them A and B, or excuse me, alpha and beta for just a moment. These angles are complementary, which is a fancy way of saying if I were to add their measures together, I would get a right angle. Working in degrees, that would be a sum of 90 degrees. Working in radians, that would be a sum of pi over 2 radians. Also going to label these 3 sides. The horizontal side, from the perspective of alpha, would be the adjacent side. From the perspective of beta, however, this would be the opposite side. The vertical side, according to beta, this would be the adjacent side, but according to alpha, this would be the opposite side. Then we have our hypotenuse. From the perspective of alpha, that's going to be the hypotenuse. And from the perspective of beta, that's going to be the hypotenuse. Hypotenuse does not change, but the adjacent and opposite sides can change. So what I want to do is consider the sine of alpha. The SO of SOHCAHTOA tells me that this is going to be the opposite side according to alpha divided by the hypotenuse according to alpha. From the perspective of beta, though, the opposite side according to alpha would be the adjacent side according to beta. And the hypotenuse stays as the hypotenuse. So from the perspective of beta, this ratio is actually adjacent over hypotenuse. Adjacent over hypotenuse tells me that that would be the cosine of beta. Now, if you made a similar argument for all of these other possible ratios, you would get that the cosine of alpha is the same as the sine of beta, that the tangent of alpha is the same as the cotangent of beta. The cotangent of alpha would be the same as the tangent of beta. Secant of alpha is equal to the cosecant of beta, and the cosecant of alpha is equal to the secant of beta. The book puts this together in a very terse statement of 5 words. 5 words? Yes. Cofunctions of complementary angles are equal. Like I said, 6 total words. That's what the book would use, is 6 total words. When they say cofunctions, what they're referring to is a pair of trigonometric functions that looks like a trigonometric function and the same trigonometric function with a co in front of it. For example, sine and cosine, tangent and cotangent, secant and cosecant. Complementary angles, again, are referring to the angles alpha and beta. They are complementary because they add up to 90 degrees. So cofunctions of complementary angles are equal. In the next video, we'll actually go over some examples where we make use of these fundamental identities.